So if you want to count us down. 3, 2, 1, go. So you can see immediately the G5 just starts pulling that data in and jamming through it. This is motion capture data we got from our good friends at Kedara. Thank you, Kedara. Motion capture data means you have a keyframe at every frame for every joint on every character. So these data files get very large. It's very important that we can push it onto the chip, do all the transforms, and then push it off to the graphics card. Two things you'll notice. Obviously, it's double the performance, but you'll also notice that the consistency of the frame rates on the Mac is much better, which is really important for animators who care about timing. So you have to have good timing if you're doing animation. So you see the consistent performance there versus the rather choppy side over here. Should we do a little bullet time homage here? Sure. Would you like to do a nice cool effect? We'll spin them around. You want a head start? Sure. No, I trust you. 3, 2, 1, go. So you see now we're doing a full 3D transform of the entire world while the animation's playing back, and the G5 chews right through that nary a hitch. So good stuff. Thanks, Brad.
Thank you, Brad. You know, I wanted to just clarify one thing. We've got a whole bunch of things in our new compilers that really optimize for the G5, but your G4 applications run without recompiling totally natively. And if you want to recompile them to pick up even more performance, it's really easy to do, as Brad just highlighted for us. Next up, Wolfram Research, Science and Engineering. And it's my great pleasure to introduce Theo Gray, co-founder of Wolfram Research.
So Steve actually goes back a long way with Mathematica. Believe it or not, it is 15 years ago to the day today that he came to our press conference to help us introduce Mathematica version 1 to the world. And not only that, today we are introducing Mathematica version 5 for the G5. In those 15 years, Mathematica has become pretty much the de facto standard language for doing mathematics in fields from physics to finance to fundamental biology. But in version 5, we're introducing features to allow you to do sort of very large-scale numerical problems, things like solving a system of linear equations with 1 million unknowns. And that happens to be exactly the kind of thing that the G5 is especially good at, the kind of thing you could really use it for. So we have a little demo here.
Hey, Dale. Do I have to be the PC again?
Sorry. So let's see, are we ready? 3,
okay.
2, 1, go. Okay, so this is kind of a little simulated real-world situation. We have it doing, on the one hand, very large integer calculations like you might do for cryptography, for example. On the other hand, doing some really large numerical matrix operations like you might use in signal processing or image analysis or things like that. Of course, we're using it to make some pretty pictures. You know, it's going, I don't know, what, twice, 2.5 times? It's going quite a bit faster. You know, often for this kind of thing, it's really not really a question of whether you could do this with a computer. It's whether you could do it before breakfast. Because, you know, I had to try a lot of different examples and figure out some parameters and things. And, you know, the kids are going to wake up. I have to get on a plane, go to California, give a demo. You often have these kind of deadlines where you need an answer today, not sometime next week. You don't have time to write a Fortran program and optimize it. You want to use a high-level, abstract, symbolic computational system, a language like Mathematica, where it'll just give you the answer. You want to use 6 gigabytes of memory? Fine. Just don't bother me with the details. I want the answer. We tried to come up with a demo where we'd actually show you the 6 gigabyte capacity, but we couldn't figure out any that wouldn't just destroy the PC. And you know, it was thrashing for a week. It'd screw up the next demo. It's not good.
As you can see from the animation that the Mac is now completed and has been done for a few moments. It's 40 steps of the fractal, and the PC is now just breaking over 20. So without breaking a sweat, the Mac has just done twice the performance.
The competition for this machine is not PCs anymore. Basically, for our customers, the competition is high-end Unix workstations that cost twice as much. It's faster than all of them, too. It's sort of... I mean, this is really the dream machine. It's got, you know, the Unix operating system that you need for anybody who's using Mathematica, who should be using Mathematica. You know, you got Unix, you got all the desktop applications you want. You've got the beautiful Windows system. It's incredibly fast. It's got a spare processor, you know, if you want to leave Microsoft Word running or something like that. And so this is where we've come in 15 years of partnership with Steve, and I don't know where we're going to be in 15 years, but I know there's going to be a version of Mathematica. It's going to be running on some kind of nanotube Mac, and maybe Steve and I will be shuffling around here to show it to you. I hope you all be here to see it. Thank you very much.
Thank you, Teo. Next up is our own eMagic, some of the most popular music creation software on the planet. And it's my pleasure to bring up Gerhard Lengeling, who is the co-founder of eMagic. Good morning, Gerhard.
Hey. Thank you, Steve. The G5 is a dream machine. It is exactly the machine all musicians have waited for. At eMagic, a lot of engineers are musicians too. Some of them are happy enough to get a machine, worked on it, did some optimizations, and obviously also did some benchmarking. And we all have been so surprised. As a benchmarking tool, we used a software instrument, a sampler, and I asked you, how many voices, how many notes do you think is it possible to play at the same time on that machine? 64, over 100. It's 1,000. It's more than 1,000 voices which can be played at the same time on that machine. This is amazing. All of the voices are high quality, 24-bit, and all of them are stereo. As a second example, if we look in studios, in professional studios, you see the big mixing consoles, very wide, lots of faders, many knobs. If you have a really huge project and you want to have this mixer now running in Logic, in software, you might want to have many EQs. Let's assume 100. 100 EQs, 8 bands each, and stereo each. This adds up to 1,600 bands. And guess what? The G5 does it. But it's even more surprising, it does it with only 25% CPU power. The new architecture of the machines benefit Logic greatly. As a music application, we handle a lot of audio streams. Obviously, the CPU power is great, but very often forgotten is the memory bandwidth. And this is very important for us. We have lots of audio streams going from one place in the machine to the other place, lots of buses, outputs, voices, everything. Many of them are contiguous. That means they don't fit in the caches. And I'm really excited that we have this machine now, that the combination of the G5 and Logic works so well. Instead of talking about music, maybe we should go for the demo. Phil?
Thank you, Howard. So again, the venerable Mac on the left and our fun PC on the right. As you know, eMagic Logic is on the Mac, and the latest version is not on Windows, so we have the most popular sequencer on the Windows side. That's Cubase. And two great products. But we've got a very complex piece here, a piece that was actually created by BT, great musician who uses a Mac, and you'll see in a minute why. And this is a piece of music created for a trailer for The Matrix. And since it's music, we're going to play the PC first and then play the Mac, and I think there'll be a noticeable difference. In addition to what you hear, for those who can see the small CPU meters in the bottom right-hand corner of each display, you'll notice something different in how much CPU they use. So let's start with the PC first and give it a first shot at this musical piece.